in Unit 2, but we are also going to mainly talk about today is more and more examples of electron configurations. With these examples in your electron configurations, it would probably be in your best interest when you see the slide come up to attempt the electron configuration before I start doing the electron configuration, especially if you think you have it down. Because as we go through them, you will want to have and or hopefully gain confidence in your ability to do these on your own as you would do that in your homework. Okay? This is, I believe, where we left off, and we are going to transition from the use of the dashes and arrows and move into a system very similar to this, where we have the numbers being given to us instead of the arrows. Okay. Ultimately, for the class, I don't really, it doesn't bother me if you prefer arrows over the numbers. You will, for mastering chemistry purposes, need to know the numbers. Ultimately, it does not matter when you come to and take our test for this class, that either or is acceptable for that. I know what both of them mean. But just know that in other places, it's always kind of one or the other. So we're going to start here. We are going to eliminate the orbital diagram part of it, though. Okay, we're not going to write that part first. Okay, we're going to have some practice on that. Orbital diagrams can be considered to be Bohr diagrams. Instead, we're going to write out 2 electron configurations for these. Okay, we're going to write out the arrow and then show how the arrow transitions or can be used to also find the number part of it. Where's a periodic table? Here we go. So, for carbon, when we look at carbon, carbon ends in what row? And if looking at a periodic table, feel free to chime in. Carbon ends in what row or period? What row or period does carbon end in? In row 2. Okay. What block is or group is carbon in? More specifically, let's go with what block carbon is in. Looking at the brackets above carbon on your periodic table. P. So that's where it ends. And we are going to utilize 3 dashes because the P block has a dumbbell shape and has 3 orientations in space. Regardless of where the element ends, all elements have to start with what? And again, that comes from reading our periodic table as if it were a page in a book. And we start in the upper left-hand corner. And it starts with 1. 1 what, though? 1s. After we read through 1s, or the first period, we then start on second row, which we know we are going to end in, but we have to get to the 2p area, we have to go through what block first? The S block. The D block does not come into play until the 4th row. So you have 2 S. And all S's have one orientation in space. Carbon has 6 protons, and in a neutral atom, as all of these will have, it also has 6 electrons. We fill the lowest energy first due to the Aufbau principle. We have them have opposite spins, Pauli's exclusion principle. And now for Hund's rule, we space them out so that they each have their own space, and we go from there. Now, what does that look like when it comes to the numbering method? Instead of arrows, we use numbers. The number is directly associated with how many arrows there are. One of the things that becomes, I think, difficult for students, and why I like to show the arrows, is it's very difficult to see Hund's rule being taken into account when you're using the numbers. If you're using the arrows, you can see, oh, they're spaced out. You can see that there's 3 orientations. Now, the numbers is easy, but sometimes I think you have to kind of know what the arrows are, kind of what would the arrow look like there as well, to kind of help with that. For oxygen, where does oxygen, what row does oxygen end in? Row 2. What block does it end in? Ends in the 2p. Regardless of where it ends, what do we have to start with? 1s. After 1s comes 2s. And some of you are going to go, there's like a really good pattern here. You're right, there is an extremely awesome pattern here. We will find again, filling in the lower energies first. Oxygen has 8 protons, so 8 electrons. I've filled in 4. Hund's rule says space them out. I now have 7. I have to now come in and pair one of them with that one. It is common to fill in the one closest to the letter with arrows. That is common practice. By all technicalities, probably could fill any of them in, but it is common practice to fill that lower end one in because it's just kind of what we do. It's the lowest one, so we would just say lowest energy. Okay? The numbers would be 1s2, 2s2, 2p4. Now, we can use our periodic tables to kind of almost guess how it's going to end as well. Oxygen ends or is the 4th element in the p block. Because if you start at boron and count boron, carbon, nitrogen, oxygen, it's the 4th element on the in that p block. That means it's going to have 4 in the p wherever it ends. Okay? Also, if you know where it ends, that means everything up to it is also going to be full. So you can write in 1s2, 2s2, and then you go, okay, now I need to figure out how many in does it go to figure out that number. Or write out the arrows. You don't need to do both unless you absolutely, well, need to do that. Phosphorus. Even though we've done these yesterday, again, it's not a bad idea to have repeated these over and over again. Phosphorus ends in what row? Row 3. What block? The P block. Okay? Just because it's now in the 3P doesn't mean that the orientations have changed any. Just because it ends in 3P doesn't mean that it's not going to change how it starts. Still has to start with 1s. And then 2s. And then 2p. 3 orientations because all p's have 3 orientations. And then, now we're in the 3rd row, but we have to start on the left-hand side of the periodic table, which is the S, 3s, and now I'm where I'm supposed to be. I go in, and I can start filling my lower energies. I now count, phosphorus is the 3rd one, following Hund's rule. I space them out and put 3 electrons. I can check myself before I wreck myself by counting up the number of arrows. The number of arrows should add up to 15. The element number, or the atomic number, should equal, in a neutral atom, the number of arrows. Or, as we see here when we do the numbers, 1s2, 2s2, 2p6, 3s2, 3p3, those numbers should add up to, the electron numbers, the superscript numbers should add up to 15. Okay? So that's kind of how, where, again, those numbers come from and how we roll with that. Now let's draw the orbital diagrams and the electron configurations. Orbital diagrams, or Bohr diagrams, or Bohr models. Okay? Now we just wrote out the electron configuration for phosphorus, so we should be able to remember that it's 1s2, 2s2, 2p6, 3s2, 3p3. But what does a Bohr model look like? If we remember back to a previous slide, we said that the Bohr model, the electrons did what like planets around the sun? They orbited, okay? So they orbit things, and so we draw these orbits. Now, how many orbits do we draw? Well, it comes down to the fact of what row is phosphorus in. It's in the 3rd row. That means it has 3 orbits. because the idea of quantization of these n values came from Bohr. And so we write 3 circles. Each circle represents a row on the periodic table. Now we place our electrons in there. Now I'm going to use red dots because that's what I'm going to use. Can you go little X's? Yeah, if that's easier, or just little circles? Yeah. Okay. I'm going to place them on these circles so that they are spaced out so that it's easy for us to see them. There's a couple ways that makes your life a little bit easier, whatever way you want. Okay? I can see from my electron configuration, I should have how many dots on my first circle, the circle inside, because that would be the ground state. That's the lowest energy. 2. I should have 2. Now we jump to the second one. You're like, oh my gosh, I have to put in 2. Then where do all the... No, remember, these numbers here tell us the row number. I have 2 2s, right? 2s2 and 2p6. The superscripts add up to 8. So I need to put 8 electrons on this dot on this second line. I space them out that way, so they're kind of there. Now, what gets a little bit crazy is in the third row, we can technically put in 18. It's like, oh, that starts to get a little crowded. Okay. Another method I've seen students do that I'm okay with is this. Both of these have 8 in the second ring, right? One just kind of has them paired up a little bit, spaced out nicely, which works. Okay? I'm okay either way. Both of those look really nice. Okay? Now in the third ring, I need to have a total of 5. Okay, that's one way. That's another way. Does not matter. It shows that you're understanding that, they do pair up. It also maybe shows that they also try to space out. I like, not everybody does Bohr diagrams or Bohr models. I like them because it leads us into something else later, and you have seen something similar to it, and it's just another way of writing them, and it's almost like a simplistic way of doing it, and you're like, oh, well, again, Peterson, making our lives easier. Let's try another one. Chlorine. One that we have not done the electron configuration for. So for the electron configuration for chlorine, it ends in the third row. Okay? So that And not only that, it's going to end with the, wrote that wrong, 3p, right? I need to start with 1s regardless. I can fill them as I go. 1s2, 2s2. Why can I put the full number there? Because I know it ends farther down the line. Okay? Now, you're like, oh, crud, how many do I put in there? Well, we have a couple options. I can count and see that chlorine is the 5th element in the 3p block. Or I can add the superscripts and go 4 plus 6 plus 2 would give me 12. And I need a total of 17. Means that negative 5, I need 5 electrons. Okay, that's another way of kind of looking at it. Right? Well, just like the previous one, we also have 3 rings. The row number. The number of rings comes from the row number. And that even works with the transition metals, and we'll see something with that. I have 2 electrons in the 1s2. I have 8 electrons in this coming out of the second row. 2 of them to the 2s, and 6 of them come from the 2p. And now I have to put 7 on the outside here. Now, some might look at this and you go, so you put 7 and chlorine's in group 17. Is there a connection between the number in the outside rings and the group number that it's in? Well, if you saw that pattern, you'd be correct that there is a pattern except for the transition metals. We call them the main group elements. That would be groups 1, 2, 13 through 18. Okay. The group number it is in, that last number, kind of tells you how many it's going to end with, or how many would be in the outside of the circle, on its outermost circle of a Bohr model. Let's try another one. Now we're getting closer to that D block. With calcium. So, calcium ends in what row? 4th row. What block? S block. Whoa, that's going far out there. Oops, that's a highlighter. I don't want no highlighter. I want the pencil. It's going to start with 1, just like all of them. Right? And then go 2p6, 3, my bad. 3s2. 3p6. I know it's filled all the way up there because it has to be, because it's in the 4th row by now. Now, calcium is the 2nd element in the S block in the 4th row. It is also in group 2, which means it's 4s2. And if I add up all the superscripts, I would get 20 of them. Now, for the Bohr diagram, or the orbital diagram, how many circles? There would be 4. Some might start to be thinking to themselves, these things could get really crowded and big when we draw one for like radon, won't they? That is correct. They do get very big and they do get very crowded. The number of electrons are still 2 in the first one, 8 in the second one. Now here's the other hint. That is their maximum amount that you can have in those. In the third, you can start to get into the D block, which means you then drop in and start putting more dots in on that third row. But I only put 8 in this one because that is all that there are. And the 3s and the 3p, add them together, I get 8. In the fourth, there are just 2 dots. Asking myself those same questions. Where does aluminum end? Third row, P block. Now that I know where it's going to end, it always starts with 1s, and it's filled, so then you go 2s, 2p, 3s. Now aluminum is in the first group, so it gets 3p1. And it's also in group 13. So in the third row, it has 3 in its outside. And also coincidentally has 13 electrons, but that's just a coincidence. Only second row P block does that even fit. It has 3 circles, for the orbital, 2 dots inside, 8 on the second ring, and 3 on the third. Okay. Let's drop down and do a really fun one, and that would be titanium. Again, try it, then we'll do it. Titanium is in the 4th row, but it's in what block? The D block. The D block is N-1. So titanium actually ends in the 3D. Normally we don't write the previous one right before it, but right before it is scandium and then calcium. And calcium ended with what? 4s. How do I get there? By starting with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, because it's the second one in on the D block. The orbital has 4 circles, 2 on the inside, 8 in the next one. Now what gets tricky is a lot of people will put their 8 on the third, and then think to put 3 on the fourth one, but it's not. You actually have to put a total of 10 on that third one, which that allows for a total of 18, up to 18 on that third circle. Now let's take a look at orbital diagram or Bohr diagram for iron. And again, always, if you have to, hit pause or just wait or try to do it on your own before I kind of show what to do, because you will find that you can learn some things for that from there. Now with the iron, we have to again look at where it's at on the periodic table, and we can see that it is in the 4th row, but it's in the D block, and because it's in the D block, we have to remember that the row number -1 is going to tell us where it's at. So it actually ends in the 3D. Now where does it start? Like all of them, it all starts with 1s. Then as we go down and over, we see 2s, 2p, 3s, 3p, and then we're now in the 4th row where we have the 4s. It fills up. Now we have to count how many over is iron, and we go scandium, titanium, vanadium, chromium, manganese, and iron, and see that it is the 6th one over. And probably should put that in a little bit over there. And now we can see that that is the electron configuration for iron. Now the orbital is going to get pretty crowded, so I'm going to minimize some things here. And so for that, we need to again have 4 rings, because it is in the 4th row, even though it might not have as many as we think. 1, 2, 3, 4. Looking at my electron configurations, I can see that I have 2 electrons in that first one, 8 in the next one. Just filling this in. Now in the 3rd row, it's probably going to be easiest to fill in as you go. So I would put in my 8 for my S and P orbitals. Fill my 4s. Then I see that I have 6 electrons from the D. and I have to place them in, and I'm going to change the color of my red here to kind of indicate that, just so that I can show you that there's 1, 2, 3, 4, 5, 6. I placed them, just kind of try to spacing things out as much as I possibly could to have that for the 6 additional ones. Now looking at arsenic. So now we're going across some things. Still in the 4th row, but this time we are now in the P block, so it's going to end with 4P. Regardless of where I'm going to end, I always have to start with 1S, then goes 2S, then goes 2P, then goes 3S, then goes 3P, and now I'm getting into the 4th row. I have to go through the 4S, and because it ends in the 4P, I have 3D10, and arsenic is the 3rd element in the P block. Now, this is the order in which the energy levels are written. There are some reference materials out there that will put the 3D before the 4S when they are filling out these as it's written there. I don't like that because I think that it confuses students in trying to figure out the energy levels that they're supposed to use. So that is why I prefer using it, doing it this way, as you should have that filled in that way. Now let's draw the orbital diagram for this. We're going to need even more room as we have. And I'll need a total of 4 rings. But my rings are going to start very quickly getting very busy. I am consciously drawing that 3rd one a little bit bigger, so I can draw the electrons in a little bit easier as I put the electrons in those lower energies first. Now in the 3rd, I am going to need a total of 18 in here. Now this is where maybe using the other method discussed before helps out, where you would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then you can just kind of place a 17 one there, maybe an 18 one there, or if you were able to space them out maybe a little bit better, that you would also be able to pair them together. Now I have a total of 5 in the outside in the 4th orbital. Now for our next one, and that would be strontium. Our next example of strontium, we can see that it ends in the 5th row in the S block of the 5th row, so 5S. Regardless of where it ends, it always has to start with 1S, 2S, 2P, 3S, 3P, 4s going through the D block, 4p all the way through that, and strontium is the second element in the S block in the 5th row, so it would have that filled outside. And as you would guess, the orbital diagram gets to be very big for this, because again, you're going to have 5 rows, and you're going to have a lot in that 3rd. Because it has 18, I draw it bigger, even though that, let's erase that there. And because I draw it, and now the 5th and the 4th one technically can not only have 18, but can have 32. We're not going to get there yet, but we will. And so things can get pretty crowded real fast. And that's why kind of knowing what you're doing helps out when you're drawing these. Lots of practice helps out when you're drawing these. As we draw them, we will find, space them all out, and there's 8, 9, 10, 11, 12, 13, 14, 15, 16, and then I'll just place 17, 18. I have to put 8 in the row again. And then in the S, in the 5th one, I put 2 on the outside. So hopefully you were able to guess some of these as we went through, and maybe or saw what you did wrong, and learned something from doing a lot of examples of electron configurations.